Hi, my name is Kanan Matharson. I'm an assistant professor in the Division of Cardiology in the Department of Medicine at Northwestern, and in this learning activity we're going to talk about how heart sounds work. This is an outline of the learning activity. The first thing we're going to do is look at a schematic overview of the circulation using a train track type of model. Then what we're going to do is take that train track and actually map it to the actual anatomy of the heart. And then what we're going to do is, having that background knowledge of the anatomy of the heart, we're going to sort of figure out how the heart sounds actually arise, the normal heart sounds that occur during every heartbeat. And then finally, what I'm going to do is extend this and just give you a little preview of how I build upon this knowledge for medical students, and so that they can understand how variations on heart sounds actually can help them diagnose various conditions. So first, let's look at that schematic. So this is an overview of the heart and the circulation. So the circulation is, as you can see, a circuit. And let's start over here when blood is just coming back from the body to the right side of the heart, which is shown up here on the top, and the left side of the heart is shown down here on the bottom. And we'll sort of walk through this. So the first thing to know is that the vena cava, abbreviated here VC, are the main veins that bring blood into the heart. And the first chamber that blood encounters when it comes into the heart is the right atrium. The right atrium is sort of a primer pump. It pumps a little bit of pumps blood into the right ventricle, and then the right ventricle pumps out into the pulmonary artery. And so that's the main conduit for blood flowing out of the right side of the heart, where it goes then to the lungs to get oxygen. And now this oxygenated blood comes back through the pulmonary veins to the left atrium, which is the first chamber blood encounters on the left side of the heart, and then to the left ventricle, and finally exits the heart through the aorta to go to the body, completing the circuit. So you can see that even though the heart is obviously one organ, it actually sort of acts as two organs in series, the right side of the heart and the left side of the heart. And the right side of the heart is responsible for pumping blood to the lungs, and the left side of the heart is responsible for pumping blood to the body. So this is the circulation. And there are important structures that give rise to the heart sounds, that is sort of the lub and the dub that you hear. And these structures are valves. And these valves are responsible for making sure blood flows in the correct direction. That is to say, when the ventricle squeezes, blood doesn't go backwards in the atrium, that it continues to move forward. So the valves open and close at specific times during the cardiac cycle, and that's what gives rise to the lub and the dub. So on the right side, between the right atrium and the right ventricle, there's the tricuspid valve. Between the right ventricle and the pulmonary artery, there's the pulmonic valve. And similarly, on the left side, between the left atrium and the left ventricle, is the mitral valve, which is sort of analogous to the tricuspid valve on the right side. And the aortic valve is between the left ventricle and the aorta, analogous to the pulmonic valve on the right side. So these valves allow for circulation to occur in the correct direction. And so here is a little train track model of the heart, and here's a little train which contains blood, and represented in these boxes the amount of oxygen. And the whole idea of the circulation is that the body, for one thing, matches oxygen, or rather the circulation matches oxygen supplied to the body to the metabolic demand here. So you can see that this train, when it goes around to the lungs, it picks up oxygen, circuits to the body, and drops off oxygen to the body in proportion to how much oxygen the tissue is demanding. So that's the idea behind the circulation. So that's a schematic overview. Now let's take a look at sort of the anatomy of the heart and map that knowledge to a representation that matches a little more closely what the heart actually looks like. So here's a drawing of the heart, and what we're going to do is actually sort of recapitulate what we just talked about on this drawing. So let's just imagine we're a little red blood cell shown here, entering in through the inferior vena cava to the right atrium. So now the red blood cell is now moved in the right atrium, and the next thing that happens is it moves into the right ventricle, and shown here is actually the contraction of the right atrium. So the right atrium contracts to squeeze blood to fill up the right ventricle even more than it's already filled. So then, now that this red blood cell is sort of in the right ventricle begins to contract, and as it contracts, the pressure in the right ventricle exceeds the pressure in the right atrium, and the tricuspid valve, shown here, closes. And the important point here is that the valves make noise typically when they close, not necessarily when they open, except in certain pathologic conditions. So here is sort of one point where heart sounds arise. So the right ventricle has begun to contract, and right now both valves are closed. And eventually what happens is the right ventricular pressure exceeds the pressure in the pulmonary artery, allowing the pulmonic valve to open. So now the right ventricle and indeed the left ventricle have squeezed, and the pulmonic valve and the aortic valves open. But let's just focus on the pulmonic valve now. So now the red blood cell is sort of in the pulmonary artery, and the right ventricle is ejecting blood into the pulmonary artery. So now the red blood cell has transited into the lungs, and I guess I haven't drawn it here, but this is the red blood cell in the lung where it's picking up oxygen. And now what's going to happen is that the red blood cell is going to enter into the left atrium. So let's see how that works on the left side. So now the red blood cell's in the left atrium. By this time, let's just say the mitral valve and the tricuspid valves have opened. Now the red blood cell is in the left ventricle. The left ventricle begins to contract. Its pressure exceeds the left atrial pressure, causing the mitral valve to close. However, at this point, the left ventricular pressure has not yet exceeded the aortic pressure, so the aortic valve is still closed. And now finally, the left ventricle, having squeezed some more, has a pressure that exceeds the pressure of the aorta, leading to the aortic valve and the aortic valve opening, and at a similar time point, the pulmonic valve actually opens because the right ventricular pressure exceeds the pulmonary artery pressure almost at the same time. So now the red blood cell is in the aorta, and it's getting ready to make its way through the body. And at some point, the aortic valve and the pulmonic valve close, leading to the second heart sound, or the dub type of sound. So that's sort of how the heart sounds arise. When the tricuspid valve and mitral valve close, that's the first heart sound, and when the aortic valve and the pulmonic valve close, that's the second heart sound. So when we kind of think of it as lub-dub, the first heart sound, or S1, is when tricuspid valve and mitral valve close, that's the lub, and the dub is when the aortic valve and pulmonic valve, or S2, close. Now the red blood cell is just sort of making its way around through the body, and finally it comes back to the inferior vena cava, and it's ready to circuit again. So that's sort of an anatomic overview of the circulation and how the circulation works. Now let's sort of map that out and think a little bit more about how the sounds are working, and what we'll do is sort of make a mock phonocardiogram recording, which is just basically a heart sound recording. So I've moved this picture over to the left here, and what we're going to do is draw a little graph, and this is the phonocardiogram, and on the y-axis is sort of the loudness, or how much noise there is, and then on the x-axis is time. Next thing we're going to do is add in a little sort of marker so we can tell where we're at on this graph in terms of time as compared to where we are at on this anatomic depiction of the heart. So, and I have a little red blood cell drawn here to sort of remind us that that's what we're mapping. Okay, so let's start this up. So the first thing that happens is the red blood cell moves in the right atrium. Then the right atrium contracts and moves in the red blood cell that we're following moves in the right ventricle. And now what happens is the right ventricle contracts, the right ventricular pressure exceeds the right atrial pressure, and the tricuspid valve closes, and simultaneously, more or less, the mitral valve closes, giving rise to the first heart sound, which we've broken up into the mitral component and the tricuspid component. So this is the first heart sound shown here in red. Then the right ventricle and left ventricle contract, ejecting blood into the pulmonary artery and aorta, respectively. Then the pulmonic valve and aortic valves close more or less at the same time, giving rise to the second heart sound, which is comprised of the aortic closure and the pulmonic closure. And just to go through that again, now the red blood cell we're tracking from the left atrium goes into the left ventricle. The left ventricle contracts, leading to mitral valve closure at a pretty similar time to when the tricuspid valve closes, giving rise to the next S1. And now the right ventricle and left ventricle contract, leading to ejection of blood into the aorta and pulmonary artery. And now the aortic valve and pulmonic valves close, giving rise to the next S2, which is divided into A2 and P2 components. So this is sort of a visual representation of what the heart sounds are like, and you can imagine that this can be a pretty useful tool for describing them to medical students. You can make the bars taller or shorter, or depending on how loud or soft sounds are expected to be in various conditions, etc. The other thing this is useful for is actually showing the timing of things and subtle differences among them. I'm just going to let the red blood cells go back to sort of the beginning. And now what I would just like to do in the closing is actually just preview a little bit about how we build on this to teach medical students. So one important thing for medical students to understand is a phenomenon called splitting of S2, that is to say an audible difference that arises between the aortic and pulmonic condition, closure, which is actually normal, and it happens in response to variations in respiration. And so knowing this normal sort of physiologic splitting phenomenon is really important, because we actually build on that, because this splitting pattern, which is a relatively simple way of getting at information, because all it needs is a stethoscope, can help us understand various conditions like electrical conditions like left bundle branch block, right bundle branch block, or congenital conditions like an atrial septal defect, which is basically a hole in the heart. So I hope you enjoyed this learning activity, and thank you very much.